In the early 20s, when the Model T was popular, a new engine was developed by Felix Wankel. He introduced the rotary internal combustion engine known as the Wankel engine. Like many scientists of those days, Felix Wankel was dissatisfied with the efficiency output of the piston engine. Besides being inefficient, the piston engine was more complicated than the rotary engine. The rotary engine, which was considered to be a dream engine, became a reality in the 60s after a study by Toyo Kogyo. The advantages of the rotary engine are, it is a simpler structure with smaller number of moving parts. There is less vibration with 3 power strokes per revolution. There is less power loss because there is no back and forth motion as found in the reciprocating engine. Being simpler, smaller, and more powerful are 3 characteristics that make the rotary engine a more attractive source of power. There is no up and down movement like that in the conventional reciprocating engine. The eccentric movement of the rotor is transferred by an internal gear to a rotating power shaft. A cutaway rotary engine in the intake position. Compression. Ignition. And exhaust stroke. The trochoid chamber in the area in which the rotor revolves. A rotor is the triangular-shaped piston which rotates in the trochoid chamber. The ignition system in the rotary engine is different from the conventional reciprocating engine. A cutaway of the reciprocating engine on the intake stroke. The intake valve opens to let the fuel-air mixture enter the combustion chamber. During the compression stroke, both valves are closed. The compressed fuel-air mixture is ready for ignition from the plug. The spark plug fires when the piston reaches the top part of the cylinder, creating a power stroke which pushes the piston downward. During the exhaust stroke, the exhaust valve is opened, allowing the consumed fuel-air mixture to leave the combustion chamber. A major difference between the piston and the rotary engine is the ignition system. In the piston engine, the spark plug is in the same enclosed area as the fuel-air mixture at the time of ignition. But in the rotary engine, the spark plug might be ignited in this early position in idling speed or in this late ignition position during high-speed rotation. There is a possibility of misfiring due to the very low rotation of the rotor in idling or to the super high-speed rotation. This could happen because the spark plug is not in the same enclosed area as the fuel-air mixture at the time of ignition. The spark plug must ignite the fuel-air mixture in the indicated position for proper firing. It is limited to 1/2 rotation on the rotor. In the Wankel engine, there are 3 power strokes in 1 revolution. This characteristic makes the Wankel engine more powerful than the reciprocating engine. If we designate the rotor as a triangle, A, B, C, with the 3 sides as X, Y, and Z, when lobe A is just leaving 9 o'clock, side X is fired. When lobe A is almost reaching 12 o'clock, side Z is entering the compression stroke. At the same time, side Y is in the intake position. When lobe A is almost reaching 3 o'clock, side Z is fired. At the same time, side Y is in the compression stroke, following side X in the exhaust position. When lobe A is reaching 7 o'clock, side Y is fired. By the time lobe A reaches back at 9 o'clock, the rotor has completed 3 firings in 1 revolution. To review the combustion characteristics of the Wankel engine, this is how the three firings occur in succession. 1, 2, 3. 1, 2, 3. 1, 2, 3. One of the problems associated with the Wankel engine is excessive vibration at idling speed. Assume that this rotor is rotating at 6,000 RPM. In slow motion, the ignition can be seen. The firing occurs while the rotor is in the late position due to the speed of the rotation of the rotor. Assume this rotor is rotating at medium speed. Here, shown in slow motion, the firing occurs while the rotor is in the earlier position. But during high speed, the ignition takes place in this position. Assume the rotor is now rotating at idling speed below 700 RPM. In slow motion, the firing occurs almost too soon to operate the engine. The ignition sometimes occurs before the compression chamber enters the spark plug area. This results in incomplete ignition, causing the unburned fuel-air mixture to be exhausted as white smoke. This defect causes the engine to jump, choke, and puff, thereby decreasing the power output. On the other hand, if the spark plug is positioned to fire correctly at idling speed, it will operate efficiently both at idling speed and medium speed. Notice the difference. This is the ignition when the engine is at idling speed. And this is the firing at medium speed. Both firings occur in the area where the spark plug is positioned. But at high speed, due to the rotational speed of the rotor, the ignition will fire too late, causing an unburned air-fuel mixture to be exhausted as white smoke. As a result of their efforts to make the rotary engine more practical, Toyo Kogyo, the Mazda automobile factory, has contributed substantially to the development of the engine. They solved one obstacle simply by adding a second spark plug, which is exposed sooner in the cycle than the plug used for high-speed rotation. Now, both spark plugs allow the engine to operate smoothly at high and idling speed. A slow-motion picture of a rotor at medium speed. Although the spark plug is positioned to operate best at high rotor speed, it still operates satisfactorily at medium speed. As the RPM of the rotor decreases to idling speed, the firing occurs too early to ignite the fuel-air mixture in the combustion chamber. To solve this problem, a second spark plug is needed to ignite the combustion chamber to get a complete ignition. The original plug is called the leading plug. This leading plug ignites first. Then the newly installed plug, which is called the trailing plug, ignites. When idling, the trailing plug does the job adequately. But at high speed, the leading as well as the trailing plugs work together to ignite the fuel-air mixture very efficiently. A review in slow motion at idling speed. We notice that the leading plug ignites first. After a time lag of a few microseconds, the trailing plug ignites. This situation does not have the undesirable characteristics of the Wankel engine, because the leading plug only fires the burned exhaust gas that would not create any explosion. In the Mazda rotary engine, the trailing plug ignites 10 degrees after the leading plug. The trailing plug is installed to operate best at idling speed. Due to the 3 power strokes per revolution, the rotary engine can accelerate easily to over 7,000 RPM, and an undesired combustion process will occur if the RPM exceeds that speed. Assuming this is the rotation of the rotor at 7,000 RPM, in slow motion, the two spark plugs ignite while the rotor is in this position. An ideal combustion process occurs, causing the engine to rotate in its direction with maximum torque. Nevertheless, if acceleration is still taking place and the rotor speed reaches about 9,000 RPM, the rotor will move to this position while it is ignited. In this case, an undesired double ignition process occurs in the two different combustion chambers. This situation creates severe damage to the engine because of the knock that occurs in the combustion chamber ignited by the trailing plug. Aero B has more power because there is an inertia force due to its direction of rotation. However, both forces are acting one against the other, causing the engine to lose power and drop its output. The Mazda rotary engine, because of its dual spark plug system and quiet performance, is an ideal engine for automobiles. The leading and trailing ignition system have their own characteristics to make the engine run smoother at both high and idling speeds. The leading plug that ignites first is exposed to the combustion chamber later than the trailing plug. On the other hand, the trailing plug, which is exposed earlier to the combustion, ignites after the leading plug. The two ignition systems are not interchangeable. Reversing the spark plug cables between plugs will cause engine failure after a period of time. A review of the dual ignition system shows the rotor is rotating at idling speeds. The combustion chamber enters the trailing plug first and the leading plug later, but the leading plug ignites first, then the trailing plug. The weakness of a Wankel engine is in its idling. Most Wankel engines that employ a single spark plug idle at not less than 800 RPM. Occasionally, if the engine happens to idle slower than 700 RPM, it will run rough and hunt. A dual-plug Wankel engine will run smoother since the fuel-air mixture will burn more efficiently at high and idling speeds. As mentioned before, a spark plug ignites a mixture of fuel and air, which burns progressively and evenly in all directions. In slow motion at idling speed, the force of the compression after the ignition is forcing against the rotation of the rotor. By employing two rotors each with two spark plugs, the idling power loss is greatly reduced. In high-speed rotation, there is no match for a rotary engine. The free power strokes per revolution make it an ideal engine. A comparison of the two-rotor Curtiss-Wright Wankel engine and the V8 reciprocating engine shows that 1/3 of the Wankel produces twice the horsepower. The V8 is 23 cubic inches larger in displacement and occupies 3 times as much space as the Wankel. The number of components and moving parts are also more in the V8 reciprocating engine. The Wankel engine being simpler, smaller, and more powerful make it more attractive as a source of power. There will be more practical uses of Wankel-type engines in the future. It will be utilized in chainsaws, lawnmowers, motorcycles, outboard motors, truck refrigeration units, and even airplane engines. Anywhere lightness and high power to weight ratio are necessities. The Wankel engine is truly the engine of the future, and it is here today.